Continuing on Chapter 36, Interference and the Wave Nature of Light, we next want to look at interference as it arises in a particular situation where light falls on a double or multiple slits, and understand how that light begins to interfere with itself and give us something called an interference pattern. One of the reasons that this is important is because it arises again in quantum mechanics, where we can take an electron and prove its wave nature by comparison with light, and the wave nature manifests itself by the interference pattern that the electron can exhibit with itself. We'll study more about that when we study quantum theory and understand that that was the proof that matter actually has a wave nature associated with it. But for now, just to get at the foundations of this, we want to look at what is called the Young's double slit experiment. And to do this, we're going to imagine that we have two holes in a slit of paper, and we have a source of light back here. So the light comes out, and we have a screen over here, and this is 36.2. And as the light goes to this point here, then of course it, as a wave does, it goes around the corner. It diffracts, and it goes that way, and this one does the same thing. And as this wave travels to this point over here, and this light travels to this point over here, we can ask, what will we see? Well, what we see is something unusual, because there's a difference in how far the light goes. If it travels from here, it goes a larger distance. Therefore, the light may or may not be out of phase with itself as it went through the other slit. So what we're interested in is what this side is right here. Well, if this is a width d for this slit, and this is, well, let's say this right here is easier to do. Imagine an angle theta. Then we end up with a triangle, which looks like this. It's a right triangle. This is a distance d, and it's a small angle. This is an angle theta, and we're interested in what this distance is over here. Let's call it x. Well, we can compute x very quickly as being d, since it's the opposite, d times the sine of the angle. So this is going to be d times the sine of theta. Now as the wave proceeds from here and from here, they will both be in phase because they go the same distance from this point forward and from this point forward. But the light may be out of phase or in phase depending upon what multiple of a wavelength this is. If only a half of a wave can get here, then of course this resulting wave will be a half of a wave out of phase and therefore destructively interfere. But if this is a whole wave here, then we would be back in phase, and this would interfere constructively at this particular angle. Of course, this angle here is the same as this angle out here, as you can quickly see by triangulation and plane geometry. So what we can see from here is that d sine theta for constructive interference, d sine theta is going to be equal to a multiple, we're using m here, of a whole wave. M times a whole wave, where m is an integer, 0, 1, 2, 3, 4, or whatever. And therefore we find that sine theta is equal to m times lambda over d, which is exactly the equation that we have right up here. And that tells us at what angles we get constructive interference. In other words, we will get bright spots on the screen. So this will be bright. If you look at the amplitude, it would look like this. But at another angle, we get destructive interference. That would be where m is 1/2, 3/2, and so forth. So if we have d sine theta is equal to m plus a half times lambda. Then we can see we get destructive because it's an integer plus a half. So it'd be 1/2 or 1 plus a half, which would be 3/2 and so forth. This is a good way to generate the half integers. And therefore, we're 180 degrees out of phase here. So here we have sine theta is equal to m plus 1/2 times lambda over d. And this is for destructive. Destructive interference. When we look at this screen over here, obviously right in the center, we're going to get constructive, then becomes destructive, constructive, destructive, and it goes like this. Likewise, it has the same pattern up here with bright regions where it's constructive and other regions where it's destructive, like right here or like right here. And these bands are an indication that we are getting, of course, interference from the difference of the two lengths that the light goes through. Now, this double slit experiment can be extended to a multiple slit experiment and have multiple slits here, and you get a similar type of effect. The next thing I want to discuss with you that's in this section is a thin film. We had mentioned this in the previous section. What we want to do is we want to look at what happens when we have a thin film. I'm going to exaggerate it now. This would be like gasoline on water. This would be water. This might be oil or gas. And this would be air. And we're going to let the wavelength in the film is going to be equal to the wavelength in the vacuum divided by the index of refraction, as we previously found from the fact that the speed of light is going to be different, therefore the wavelength is going to be different for the same wave. So as this wave comes in, it's going to reflect from the bottom and it's going to reflect from the top. And we're going to compare these two. The difference is going to be of the distance between the top and the bottom. First of all, in the top, let's look at the top, it's going to be twice the thickness. I'm sorry, I'm doing the bottom first. In the bottom, we have the thickness going down and the thickness coming up. So we have twice the thickness as a difference in distances, plus 1/2 of lambda in the film due to reflection. Now this is an unusual effect, but when the wavelength reflects in the film off of the water, then you get a 1/2 of a lambda shift in the wave. And this is going to be compared to what? This wave right here, which reflects, and there is no shift here due to the half of a wave. Pardon me. There is a shift here due to the half of the wave also, but not due to the thickness. So at the top, we only have 1/2 of lambda of the film, or 3/2 for lambda of the film, and so forth, if we get constructive interference. Now, by subtracting 1/2 of lambda of the film from each side, we get twice the thickness, or 2t, and that 2t is going to be equal to half the film over here subtracted with this will give me 0. Here, 3/2 minus 1/2 gives me 1, 2, and so forth, times lambda of the film, or the thickness is going to be equal to 1/2 of those. So where the thickness is, twice the thickness is equal to that, so then we can say when the thickness is equal to an integer over 2 times lambda of the film, the wavelength of the light in the film, then we will get constructive interference. Now you can see that this is going to be, for different wavelengths, we're going to get constructive interference in different places. And so we see these various shimmering colors due to the fact that the wavelength of blue and the wavelength of red and so forth here are different.